simple. The solution is actually not quite that simple. So we're saying we have a relationship between x and y, that's y equals x to the power 3 plus w, with x and w being independent normal, right? And we want to find the minimum mean square error solution. So the fundamental principle that we're going to apply here is what we mentioned last time, that the error, the residual error, is orthogonal to the solution. So we therefore can say that, well, first of all, our expectation of x minus x hat is 0, which so that just tells us that we want to have that the estimator is going to be unbiased, and we want to have that the expectation of x minus x hat, x hat times y is 0. And that's the orthogonality between the residual error that we have to our y. So from that, we can conclude, first of all, that b equals the expectation of x minus a times the expectation of y. And we furthermore know that a is the covariance between x and y and the variance of y. Now, in order to compute this covariance and variance, we have to start looking out for the moments that we are going to encounter, in particular the moments of x. And for the moments of x, you have to remember that for a Gaussian, the expectation of x to the power of 2k is 2k minus 1, double factorial. You remember we derived this once upon a time, and we also established the notation for this double factorial. And the expectation of x to the power of 2k plus 1 is 0, because we have a symmetric distribution, like the normal distribution symmetric around 0, and all odd moments for such a distribution, of course, are 0. So with that information, we know that the expectation of x to the power of 4 is 3, and the expectation of x to the power of 6 is 15. Now, let's look at the expectation of x, which is equal to the expectation of w, is 0, as per our problem statement. And we've got IID, we've got independent zero mean Gaussian, so of course that expectation is 0. And the expectation of y is, due to linearity, the expectation of x to the power of 3 plus the expectation of w. And so this is an odd moment of x, this is another odd moment of w, so that's again 0 in our state. Okay, so now we know first moments. Now, and this is what we need here. Right? Now we have to look at the covariance. So the covariance of x and y is the expectation of xy, which is of course the expectation of x times x to the power of 3 plus w, and I'm just substituting here, which is expectation of x to the 4th plus expectation of xw, and that is this, we just computed here, right? That's 3. This here is, since x and w is independent, it's the expectation of x times the expectation of w, which is 0 times 0, so this is just 3. The variance of y is the expectation of y squared, and so that's the expectation of x to the power of 3 plus w squared, which is expectation of x to the power of 6 plus 2 times expectation of x to the power of 3 times w plus expectation of w squared. And expectation of x to the power of 6, we computed here, that's 15. Expectation of x to the 3rd times w, that's again product of expectation of x to the 3rd and expectation of w, right, which is, this is again 0 times 0, and expectation of w squared is 1, so this is 16. And therefore, our estimator is a equals covariance of xy divided by the variance of y squared, so this is 3 divided by 16. And b is expectation of x, right, which is 0, minus a times expectation of y, which is also 0, so that is, of course, 0. And therefore, our LMMC estimator is x hat is 3/16 times y. Okay, so we will today continue still a little bit more in terms of estimators, and I'm also going to talk about ergodicity. So if you're wondering how we are aligned with the syllabus, we are about one lecture behind, so we might actually deal with Markov chains in a little bit shorter way, probably just one lecture instead of two compared to the originally anticipated version. Now, before we jump into today's thing, I wanted to address a question that I received, and that I think goes more or less to the core of what this course is about, and also about how you best prepare for the exams. And so the question was, and I'm paraphrasing here, well, why are we spending so much time on the theory, and we're not really doing that many recipes for solving problems? And if we do, well, then the homework is different from the recipes for the things that we're learning in class, and it's again, we need different recipes than what we had in the homework. So the answer to that is that this course is not trying to give you recipes. And this course is here for you to understand the fundamentals of probability and how you design your own recipes. That's a very big difference. And you might be accustomed from some introductory math courses of, oh, it's always the same type of problems, and you know exactly, I take this algorithm, I plug this in here, and I go according to a particular scheme. That really doesn't work here for probability, or actually for most of the more advanced math, for two reasons. The first one is probability has so many different applications. Right? Maybe we can do 50 different recipes in this course, but you will need 1,000 in your lifetime, and we cannot cover all of the things that you might encounter. And so the only way to really give you the basis for your work is that you understand the principles, and you design your own stuff depending on the situation that you need. And the second question is, and this affects you more or less directly once you go to the courses in the next semester, because as you, I'm sure, know, and that's probably one of the reasons why you're in this course, is that probability is the prerequisite for most of the courses in, be it control, signal processing, or communications. Right? There are so many different things there. You need to be able to pull out the principles you learned here and apply them. The other thing is going to just affect you later on in your career. Right? And this has become especially relevant in the age of large language models and ChatGPT and similar things. And problems that can be solved by a recipe. Anybody can just type in the prompts into ChatGPT and you get the solution. Right? No company is going to hire you to solve that sort of, or to proceed with that sort of work of just saying, okay, I know a recipe, I'm going to take the values, I'm going to plug this in here. So what we're trying to do here is really prepare you for a world where you're saying that, well, you have to tackle the problems that are not according to recipe, where you have to come up with your own solution methods. And for that, you'll have to go to those principles, combine things in the way that you need, and then come up with a solution for these advanced problems. And so that's, if you, after this course is over, you say you have maybe a basis for that, which of course you will have to practice and apply continuously, then that has really achieved the goal of this course. And if you're just saying that I know how to solve problems of how many different model combinations there are when I put the models back into the bag, no, that's not what what would be really a good outcome from here. And why am I saying this is relevant for the preparation of also the exams, and in particular now the finals, since that is the only exam that is left. And so when you are practicing homework or just sample examples from the books, right, try not to see too much of, well, what is the recipe here, but try to say, okay, what are the principles that I need to apply? Of course, it's related to the equations, to the theory that we've learned, right? But you have to figure yourself out from the problem statement, okay, do I need to apply here independence of the variables or special properties of geometrical variables or whatever is needed to be done here, and not just try and see, is there some algorithm or some recipe that I know that I can plug in here. So that's hopefully going to help you a little bit also in exam preparation, that you know what is it that you should actually train here for. Any questions concerning this? Okay. Now, that being said, I'm still going to jump into an example now in which we're actually first going to deal a little bit more with the different hypothesis tests that we were discussing last time, just to point out to you what are the different results that we can obtain. And so the example here is we have a disk drive factory, and manufacturer and the failure rate, meaning that a randomly chosen drive is just not working, is normally 10 to the power minus 4. However, on average, every 10 days, there's a problem cropping up in the manufacturing process, and the failure probability jumps to 10 to the power minus 1. And the quality assurance inspector should test just the drives that are coming off the air, off the manufacturing belt, and they are going to test n drives every morning. Right, so this problem would always come up overnight, and when you restart it, suddenly you've got the bad failure rate. You're testing n drives, and you're checking how many of those n drives should I test so that I know whether it is a problem day or it is a regular day. So there are now a lot of different ways in which this problem can be solved. Right? So fundamentally, we have a hypothesis test. Right? The hypothesis says, is it a normal day, is it a problem day? And we do know, first of all, because of the statement on average, every 10th day is a problem day, the probability for hypothesis 0 is 0.1. Sorry, hypothesis 1, with saying that is the probability, which is, of course, 1 minus the probability of H0. And the first solution that we can make is we're doing a map estimation. So we're saying n is considered to be A0, which means regular day, if the probability of, sorry, n conditioned of H0 of n divided by the probability of n conditioned of H1 of n is larger or equal to the probability of H1 divided by the probability of H0. And then we also know that the probability of n conditioned on H1 is Q1 times 1 minus Q1 to the power of n minus 1. And so we have to think back quite a few weeks or even a month back, and we said, well, we're flipping a coin, and we're saying, how long does it take until the coin comes up heads for the first time? Right? Same thing here, and we're testing a disk or a sequence of disks, and we're saying, how long does it take until a disk is faulty for the first time? Completely equivalent mathematically. It's a geometrical random variable, and this is just the equation for the geometrical random variable. And so this is our likelihood that a problem disk has cropped up by the nth disk that we have tested. And so the equations are, of course, completely equivalent for hypothesis H0 and hypothesis H1, because the only difference is what that failure rate Q is, or in terms of flipping the coin, right, what's the probability of heads coming up is in this case here. And so these are our probabilities for the two hypotheses. And we have furthermore the probability of n conditioned on H0, and then we have the probabilities for these two hypotheses to occur. These are the a priori. Yes.
I just have a bit of question now regarding our questions. I think my understanding was that we test n drives. So should we use like a binomial distribution for that? We test n and not know like this n failures all the time.
No, sorry. The question is we continue testing until the first failure occurs. And so the question is just if no failure occurs, how long should we be testing until we are saying that okay, there is no failure in that batch, and therefore we are thinking it's a normal day. Yeah, sorry, the statement was not quite precise that I made at the beginning. And yeah, so with these two pieces of information, and we actually already have an implicit equation for our n here. And so we just need to do a little bit of reformulation, which I'm not going to go through here, but we're basically just deciding that if n larger equal n star, which is 1 plus the logarithm of q1 p of h1 divided by q0 p of h0 divided by the logarithm of 1 minus q0 divided by 1 minus q1. That gives us an n star of 45.8. So that means, again, to bring it back to the original problem, that the inspector tests 46 drives, and if in those first 46 drives there is no failure occurring, they declare that today is a normal day, production doesn't have to be halted, and we can proceed. And if you're actually interested in the error probabilities, and probability of a false alarm, meaning that we're declaring it's a problem day even though everything is fine, well, the probability for that is that n smaller equal 45 condition on hypothesis 0 actually holds, which is 1 minus, then we have 1 minus q0, which is 10 to the power minus 4 to the power 45, which is 0.0045, and the probability of a misdetection is 1 minus 10 to the power minus 1 to the power 45, which is 0.0087. So that was the maximum a posteriori test, and we said in a certain sense that is actually optimum. However, from a practical point of view, right, if you're running the factory, you're actually interested in, well, what is the detrimental effect of a false alarm? What is the detrimental effect of a misdetection? False alarm typically would mean that you're halting the production line, you're verifying whether everything is working, so during the time you're not producing, you're incurring a certain cost. If you miss the detection, if you have a misdetection, then you're sending out a whole bunch of failed drives. Customers will come back to you, you have to deal with all the returns, shipping of the proper devices and so on, so there is a cost associated with that as well. And so let's just say we have a certain given costs, and we want to know what is the actual optimum testing when we take those costs into account. And so minimum cost. So we're saying that false alarm has a cost 30-minute loss of production. We're just saying this is $50,000. And then the misdetection, because you're shipping out 1,000 disk drives that are erroneous or that are faulty, the cost is $200K. And therefore, when we're now doing our hypothesis test, we said the equation is actually doesn't look very different from what we had for the maximum a posteriori. It's still like this: probability of H1 divided by probability of H0. Just that now this gets multiplied with probability with the cost of 0.1 times the cost of 1.0. And when we're going to plug in those values, right, again, I don't want to spend all the time rewriting equations. All you need to do here is multiply P of H1 with the costs for and P of H0 with the cost of false alarm and misdetection. And when we do that, it's going to turn out our n star is going to become 58.92. So you now need to test 59 disks, right, which is quite an increase compared to the 46 that we previously had, and that's just rooted in the fact that the cost for a misdetection is higher than the cost for a false alarm. And if it were the other way around, obviously the number of disks that we need to test would go down. And when we're again computing the failure probability, so the probability of false alarm, and again it's the same equation, just instead of to the power 45, we're having now the power 58. We are getting 0.0058, and the probability of misdetection is 0.0022. And so you can see that in contrast to this case, map case where the false alarm probability was lower than the misdetection probability, this has now flipped around, again completely in line with our intuition that, well, if the misdetection has a higher cost, we're going to reduce the probability that, that we have as such an error probability in our case. And if we want to do the whole thing with maximum likelihood, then we just pretty much ignore the a priori probabilities that we see here. And so we're just going to say our P n conditional on h0 of n divided by P n conditional on h1 of n should be 1. And again, we plug this whole thing in. And now we're requiring our n star to be 66.62. So we need to test 67 disks. And the reason for that, again, if you're just trying to tie this to your intuition, is that we are not taking into account the a priori probabilities, meaning in the math estimator, we know that a bad day is less likely. It only has a 10% likelihood compared to a normal day with 0.9 probability. Right? Therefore, under maximum a posteriori, we can reduce the number of disks that we use, that we test. Whereas in a maximum likelihood test, we're just saying, well, we want to fulfill this equation here. We have no a priori knowledge, therefore we have to do more tests. And this is going to lead now to a false alarm test, which is false alarm probability of 0.066 and a misdetection probability of 9.55 times 10 to the power of minus 4. Now, the cost that you would incur with this particular test here is, of course, higher than what we would get with the minimum cost test, but interestingly enough, not very much higher. I'm not going to write down all the numbers here, because the specifics of the solution very much going to depend on well, what is the cost ratio and so on. And so in this particular example, you get I think $300 versus a $290, but it really depends very much on the example. But generally speaking, maximum likelihood is very popular because you don't need that extra knowledge about a priori probabilities, and you still get to a solution that's fairly close to a maximum a posteriori estimator. Okay, so that was just one example of how we're dealing with the various hypothesis tests. Now, coming back to our linear estimators. So remember that last time we were going through the details of how we do our linear estimation. We started out with just saying we have one variable depending on a second random variable, so a scalar y correlated with a scalar x. Then we went through a vector y condition on a scalar x, and finally a vector y condition on a vector x. And the equations were all fairly similar, it's just that we ultimately ended up with a relatively complex equation that, say, gave us in a matrix form. I'm going to rewrite this because it was at the very last minutes of last time. We have our estimated x being the covariance matrix between x and y, so the cross covariance matrix, multiplied with the autocovariance matrix of y, then multiplied with y minus its mean, plus mu x. Again, for the final exam, you're not going to get an exercise that is going to involve vectors, because that just takes too much time for the algebra. Right? But for your actual life, it's very important that you actually know what the vector formulations are, because that is what you're normally encountering in practice. And then it doesn't, again, matter whether these are samples from some biological experiment, whether these are general estimates you're getting in a multi-carrier signal in wireless communications. Usually you have a vector of x's and a vector of y's that has some correlation between them. And in terms of how do you remember this equation, or how do you interpret that? Well, first of all, we're saying that, well, we should consider not the actual random vector y, but we should first subtract the mean from it, and because it's the random variations around the mean that have essentially the correlation or the covariance with the variable x. And so we subtract the mean of y, and then at the very end we're going to add the mean of x back to it, because that makes sense for getting our x here. Now, you have to divide by the autocovariance matrix of y, because if two values of y are very strongly correlated with respect to each other, they give you, you get reduced value from those two values together. And you can basically just say, well, y1 and y2 are extremely correlated, so I cannot say y1 gives me information about x and y2 gives me information about x, because y1 and y2 basically carry the same piece of information. And that's why you essentially have the inverse of the autocovariance matrix here. And the cross-covariance matrix between x and y, that's pretty obvious. Right? I mean, the more strongly x and y are correlated, the better you can estimate how the deviation from the mean of y impacts the deviation from the mean of x. And this is, of course, all just a very hand-waving intuitive interpretation, but we did give the derivation of that last time, the mathematical derivation, so this is just an additional help for you to remember and to interpret the results that you see here. So a little bit of additional notes. The first one is all of this was done in order to minimize the MSE. And as we discussed last time, right, the mean square error is a useful criterion. We often experience it in practice, but it is not the only criterion. So in particular, if you want to minimize the mean absolute error, which is also known as the L1 norm, and then you can do that as well. The drawback is you're not getting a nice closed form equation like this, but you have to solve a linear program. Now, linear programs are still quite acceptable in terms of numerical complexity, and because those are, you're basically solving a complex problem, you know you have polynomial complexity, but it might still take more time than what you're doing with mean square error. And linear regression is one of the core problems that you're actually encountering in machine learning. And typically during the training phase, you essentially, if you have supervised learning, for example, you are learning the covariance matrix during the training phase, you're applying it during your testing phase. So this is as a standard machine learning issue. Now, just like in hypothesis tests, we also have other estimators in a parameter estimation problem. So we can consider, for example, a maximum a posteriori estimate, where we're saying we want to get an x hat, MAP, of yj, which is the argmax over all the x element of our testing of our set omega x of p x conditional y, x conditional on a particular yj. And so when we're saying we want to find our best estimate of x given a particular y that we're familiar with, and this is our conditional probability. We're saying that, well, what's our probability that we get that x is the true value given that we're observing a particular y. And we are basically just running through all the different possibilities in our set and saying, well, what is that? That's a MAP problem like we've encountered many times before. Now, if this is just a scalar problem, then all the tools that we've applied previously and all the examples apply here as well. And so imagine that you're sending digital data over a noisy channel, then you're essentially just saying, well, our estimate of which bit was actually being transmitted. I'm saying, well, what's the likelihood that x was transmitted conditioned on that I'm seeing a particular y observation, and you're running through all possibilities of what the transmitted bit could be, which would be just 1 and 0. And then, of course, there are other situations in which this problem is much more complicated, but the fundamental principle here stays the same. And similarly, we have our maximum likelihood estimate of x yj Now, it's very important that all of these estimators can be applied to the question of unknown parameters of a probability mass function. And so we can, for example, we've dealt for a long time with the question of, well, what is the expected value of a random variable, given that we have a set of observations. And then we usually always said that, well, we just take the sample mean and that's our estimate. But now consider the situation that you have a bunch of observations, and you say, well, I know I should be fitting a Weibull distribution to it, which has the parameter gamma in it. And what is the best way to estimate the gamma? And that is a question that is not obvious, and where one of these estimators can actually come into play, right? Because you can say that, well, my x here would be some sort of parameter. I have a set of observations y. How am I actually getting my best estimate in the map sense, in the maximum likelihood sense of these parameters? Now, that very likely is not going to be a problem you can solve via linear regression, unless somehow that parameter depends linearly on all of your observations. So we have to think about it a little bit more carefully. And I'll give you a first example. But before we get to that, I'm going to talk about the so-called likelihood function. So we're denoting an unknown parameter as, which could be one of those like gamma parameters in Weibull or whichever, as theta. Now the likelihood function is an n-dimensional density function where we first of all saying we have n observations with a density function f of x1, x2 to xn, which are our observations, and theta. And since the observations are independent of each other, that is f of x1 theta times f of x2 theta times and so on, f of xn theta. So for the likelihood function, we're now thinking of this function as a function of theta with x1, x2, xn as parameters, as known parameters. Let me maybe first. And this is simply now called the likelihood function L of theta. We're not writing explicitly anymore those parameters x1 to xn down, right? Because we're saying, well, those are observations. This is what we have as our input. We want to now find out what is actually the theta. And also, often very handy, is the log likelihood function, which is small l of theta, which is log to the base of e. We can define it for other logarithms as well. And so, for example, in digital communication, you usually make this log to the base of 2. So in the future, I'm just going to write log, and you pick whatever base you want, of L of theta. So this is just the preliminary, or this is just a mathematical preliminary, just a definition of the likelihood function that we're going to need now for the next step. So now let's go to the example. And we're saying we have a Poisson probability mass function with an unknown parameter lambda. So in this case, theta equals lambda, right? And so now we're saying we have a whole bunch of observations, x1 to xn, and we want to find out what is the correct value, or I should say our best estimator of the lambda given our observations. So in order to do that, we are writing down the likelihood function, and that is now just the probability density function, which is the Poisson distribution, right, with a given observation x1 and an unknown parameter lambda. So we have lambda to the power of x1 times e to the power of minus lambda divided by x1 factorial. And so this is just the standard equation for a Poisson. The only unusual thing here is that now lambda is the unknown and x1 is the known. But otherwise, right, formally, there is no difference to what we've always had. And so this is the first observation. Now that gets multiplied, as we said here, with the f of x2 until f of xn, and lambda to the power of xn times e to the power of minus lambda divided by xn factorial, which you can write as lambda to the power of x1 plus xn times e to the power of minus n lambda divided by the product of equal 1 to n xi factorial. Now, because we have here products something to the power of x1 blah, 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 it's pretty obvious that we should move on to the log likelihood function. And so we're taking just the logarithm of the thing we computed up here, which is x1 plus xn times the logarithm of lambda minus n lambda minus the sum of 1 to n of the logarithms of the xi factorial. So I think you know the logarithm rules. This is just writing the logarithm in front of this and applying the logarithm of exponential of x to the power of a is a times logarithm of x, and so on. So now we want to see what is the lambda that maximizes our log likelihood function. And so you might wonder, well, we said we want to maximize our likelihood function. Why are we now maximizing the log likelihood function? Well, because the logarithm is a monotonic function. Therefore, if you find the maximum of the log likelihood function, you found the maximum of the likelihood function. So all we need to do now is to say, well, let's take dl of lambda with respect to lambda, evaluated at lambda equal lambda hat. So this is now x1 plus xn divided by lambda hat minus n is 0, and this is our definition of the maximum. And from that, it now follows that lambda hat is x1 plus xn divided by n. So in other words, the optimum estimate of lambda is just the sample mean. This is not a completely surprising result, because the expectation of a Poisson variable is just lambda. So therefore, we can anticipate that if we look at the sample mean, which is the best estimate of our expectation, we're also getting the best estimate of our parameter lambda. But that second argument that I brought is a sort of hand-waving justification. This here is actually a proper mathematical derivation of how you get to it. But you might now wonder of, well, is that all that we can get with this sort of thing? A justification for something that we already know anyway? And the answer is no, there are more complicated problems that you now can solve properly as well. And the example I'm giving you here is the censored lifetime test. So the concept of censoring in experiments actually plays an important role in a lot of different things. It essentially just means that you don't have the opportunity to observe certain extreme realizations of your random variable. And so in the example I'm going to bring here now is that, well, we are looking at the lifetime of light bulbs, and we want to observe pretty much how long that is. And if we are unlucky in a sense, there might be light bulbs that burn for a really, really long time, and we just have to make this experiment longer than we actually have time. And so at some point we will want to stop and say, okay, at this point in time we stop our observations, we just know that there are still 3 light bulbs out of 1,000 burning by this time, and we're not going to find out the exact time of when they are actually burning out. And in my own work, I encountered a very similar situation where we said, well, we are measuring received signal power, but if that received signal power falls below the noise threshold, below the sensitivity of our measurement instrumentation, we are not measuring anything. Now, you have to take these points where you're not measuring anything into account in your overall analysis. If you just disregard them, right, you get the wrong result, because there is information in the fact that you cannot measure it, right? Just like there is information in the fact that there are still light bulbs burning by the time you stop your experiment. So how do we phrase this whole thing now mathematically? So we're again saying we've got IID exponential lifetimes. So therefore, and we stop experiment at time capital T. we're saying our probability that a bulb reaches time t is lambda times e to the power minus lambda t, and the probability that, we stop it at time t max. So the probability of the lifetime t is this. The probability that time t is larger than t max is then, of course, e to the power minus lambda times t max. So our likelihood function now looks as follows. And it's the product of ft of ti, and which are our observations of the lifetimes for all the bulbs that burn out during our observation. And we assume that there are k bulbs that burn out during the observation. And then there we can observe the exact lifetime, the ti. And then multiplied with the product over all bulbs that are still alive by the time we stop the experiment, where we now can just say, well, we know that this has to be the probability of t larger than t max. And we know these bulbs have some lifetime larger than t max, and what that lifetime is, we don't know, but we can just say, well, we know its probability density function. And so this can be now rewritten, of course, as I equal 1 to n minus k lambda times e to the power of minus lambda ti times the product of I equal n minus k plus 1 to n e to the power of minus lambda t max, which is lambda to the power of n minus k times e to the power of minus lambda t1 to t plus 2 tn minus k times e to the power of minus k lambda t max. Therefore, the log likelihood function is n minus k times logarithm of lambda minus lambda times t1 plus tn minus k lambda t max. And this is, again, just algebraic manipulations. And therefore, we get our estimate lambda hat as n minus k divided by t1 plus tn minus k plus k t max. And you'll notice the difference in this result from what we would get with any naive approach. And if we would just say, well, let's ignore all the light bulbs that are still alive at the time, and simply say we do not count them, then we would just have the wrong denominator. We're just completely off with our estimate. And if we would just set the lifetime of the long-lived bulbs to t max and say every bulb that's still alive at t max has a lifetime of t max, then if you plug that in, then you actually get n divided by what we have here as the denominator, which again would be obviously quite wrong. So you need to really do your full derivation here of the log likelihood function in order to get the correct estimate of the censored results. It's not something that you can do in another way, in a sort of more simple or more intuitive way. You just have to go through the steps of deriving your maximum likelihood estimate. Okay, we're already past our usual break time. Let's take a 5-minute break until 9:16. Then we're going to get to Bayesian estimation. Okay, let's resume. And yeah, because the question has repeatedly come up about what is the recommended accompanying text to read. And I think I mentioned a couple of times there is not a single book where I would say this contains everything, and the material I'm presenting here is pulled together from different sources. But I would say that for most of the earlier material, up to and including the continuous random variables, Gubner is probably the closest to what I'm talking about here, with some of the examples, or you can also look at Yates, and it gives, as I mentioned, a lot of nice examples as well, but the theory is pretty well explained in Gubner. For parameter estimation, hypothesis testing, and all of these things, I actually prefer the way that it is presented in Yates, and it's a more detailed description, more examples that are going with it. And just also a heads up, when we're then finally going to come to the random processes, then Ross really gives the most detailed explanation. Now, I have to warn you, Ross spends about 300 pages on the random processes. Right? There is a whole course, 562, that is dealing only with random processes. Right? You're obviously not going to be expected to know everything that's in there, but and so you certainly can look at the pretty brief representation in Gubner also for some of the material there. But if you need more detailed explanation, if you're not sure after reading Gubner, well, what does that mean? What does that mean? Then Ross certainly is a good resource. Some of the material that I'm presenting here is just not in any of the textbooks at all. And so when we're later on today going to come to the concepts of general capacity and entropy and so on, then, well, that is, of course, in various textbooks on information theory, but I wouldn't even suggest that you start reading about this, because there will be so much overhead in just getting all of those fundamentals just in order to read about 2-3 pages of the stuff that we're doing here, that I wouldn't say this is very effective for you.